Okay, I've got that on the
Okay.
screen. You can proceed. And welcome.
All
Thanks.
right. Yep. Welcome. So I'm going to talk about game physics, and so I've been creating a physics engine inside of Roblox recently, and well, my main motivation for doing so was just to learn how physics engines work, and I decided to do it inside of Roblox because that's just what I'm most familiar with. Um, I probably wouldn't use this engine for a real game though, because Roblox already has a physics engine that's actually pretty technically impressive. A lot of players they meme about Roblox physics being broken and stuff, but it's actually pretty um, impressive piece of technology. The fact that it can run over the network as well and replicate and stuff like that. Um, However, this physics engine is generally applicable, so uh, the things the concepts I'm going to present today can totally be implemented in any environment. Um, so for game physics specifically, it's we don't really care about accuracy as much as we would for if we were simulating uh, something more rigorously. So 60 hertz is usually fine. Game physics run a number of times per frame. They update a number of times per frame. So running game physics at 60 hertz is usually fine, um, assuming that most people play games at 60 frames per second. This means you have one physics step per frame. And in game physics, you can take many shortcuts in order to speed up the simulation, considering that it needs to be able to update the whole physics world in under, if we're running at 60 FPS, that must be like 16 milliseconds. Um, so as long as everything looks believable enough, everything is good. So first off, I'm gonna define a few terms. So a rigid body it's just a physics object essentially. And it contains properties like mass and bounciness and friction. Also, an inertia tensor, and the inertia tensor in this case is uh, defined as a 3 by 3 matrix. And I'll talk about the inertia tensor in a little bit, um, and what that matrix free.new thing, what that is, because that isn't a default Roblox type. Then we also have. Can you see my mouse, by the way?
Yeah, looks good.
Yeah. Okay. So it has. I also have a C-frame property for rigid bodies because that's kind of convenient. Because Roblox already has that type, and we have a position, a velocity, angular velocity, and then we have force and torque accumulators, which I'll talk about later as well. These can be thought of as like the net force acting on the object in a particular frame. And then when we create our new rigid body, we also update the inertia tensor. And again, I'll talk about this a little bit later. So rigid bodies also have a, there it is, physics shape or collision shape. And collision shapes are defined like this. So I have two examples here. I have a sphere and I have a box. So a sphere is just defined from a radius. So I have a shape type, which is just used to identify which type of shape it is, and a radius. And for each of these two classes, I also have a from part constructor that just constructs a physics shape from a part. So for the sphere, it just takes the x size. It doesn't really matter which one it is. Roblox, when you scale a sphere, it automatically constrains the size, so it's uniform on all axes. So it can be any x, y, or z, and then multiply that by half. And I also have two methods for getting the axis-aligned bounding box, which is also useful for, which I'll also talk about later. For the box shape, it's just defined with a half extents, which is just a part size times 0.5. And yeah, so all of these rigid bodies are contained in what I call a dynamics world. It's just you could just call it a physics world or whatever you want. So the dynamics world holds all the rigid bodies in an array, and it also defines some properties like gravity, some global configurations like gravity, and also the time step, which I have set to 1/60th. And then I also have a collision world, which is used for broad face, which is used for generating contact pairs. And I'll talk about that also in a little bit. Okay, so let's talk about integrating physics. Oops. So a physics engine uses a semi-implicit Euler method, which is if the position of an object is x, then we can update the position using Euler's method with t plus some delta time, and this will be equal to the current position plus the velocity of the object at this point times your delta time. And for the object, or sorry, for the orientation of an object, it's the same thing. We can update that with the orientation plus the plus omega, which is the angular velocity. So v is linear velocity, omega is angular velocity times delta t. Now with orientation, is a little bit different in 3D because orientation is not defined as a vector, but a 3x3 matrix. So instead, what we do is we can use an axis angle rotation matrix, where we take the angular velocity normalized for the angle or the axes, and the angle will then be the magnitude of that angular velocity times delta t again. And then we just transform the the orientation by that rotation matrix. All right, so forces and torques. So when you apply a force to an object or to a rigid body, it's going to change its velocity, and possibly, depending on where you apply the force, may also change its angular velocity. So each force application corresponds to a resulting torque, which I have denoted as tau of t. So if the torque is non-zero, then the angular velocity is changed. And so the torque can be defined as the cross product between the vector from the center of mass to the force application point. I see I've actually flipped this vector. It's supposed to point from the origin to here, but yeah.
So the center of mass is a thing you just set up separately for the different, was it collision types? Was that the kind of bodies you
Yeah.
had? Mm-hmm.
Yeah, so for my collision types, the center of mass is just assumed to be the center of like the geometric center of the shapes. So the center of mass of a sphere will always be the center of the sphere, and same for the box. So yep. So there we can, from a force and an application point, we can calculate the resulting force and torque. So we have mass, And mass determines how hard it is to move an object. And mass is a scalar. And inertia is similar to mass. It's often called rotational mass, and it determines how hard it is to rotate an object. And the inertia tensor, or the inertia, is a free by free matrix, and it's called the inertia tensor. And you can find a list of inertia tensors for common primitive shapes online, or how to calculate them. And yeah, so Roblox does not have a matrix type like this. We have C-frames, and C-frames use free by free matrices for rotation, but they don't have like an inverse operation. But they do, but it's actually a transpose and not an actual inverse calculation. And we're going to need to take the inverse of the mass and the inverse of the inertia tensor at some point. So I've actually implemented my own matrix, my own free by free matrix class that implements an inverse operations, and that's what I use for inertia tensors in the engine. And so momentum and impulse. So the integrals of force and torque over time is defined as linear and angular momentum. So yeah, so this is, first of all, this is momentum, which is defined as mass times velocity. And that is like how difficult it is to change an object's movement. And so a change in momentum is defined as the force times, well, this is using Euler's method again. Force times some delta time is a change in momentum. So if we want to calculate a change in velocity, we can rearrange this formula or combine these formulas to take the inverse of the mass times your change in momentum, and that results in a change in velocity. And similarly, for a change in, well, this would be angular momentum instead of linear momentum. So angular momentum is defined as the inertia tensor times, or multiplied by the omega, which is the angular velocity, which is a vector. So this is a matrix vector multiplication. And a change in angular momentum would be a torque, or the torque of the object multiplied by a delta time. And so if you want to calculate a change in angular velocity, you can use the inertia tensor. And I have this little equation here where Q is the rotation matrix of the object. So because the inertia tensor is local, it's defined locally for the object, because as an object rotates, its inertia actually changes. So we have, this is what is known as a local inertia tensor. So this operation here, where we transform the inertia tensor into the global space, or the world space, essentially, by multiplying it by the rotation matrix of the object.
Probably worth commenting that QT, the transpose, is the inverse.
Yeah, that transposes. Yeah, right. And finally, we multiply by the the change in angular momentum, and that gives us a change in angular velocity. So I have a little demonstration of mass at play here. And you can kind of see you can see as the small object is hitting the large object, it's losing a lot of its momentum because the middle one has more mass. But then if you introduce another object with a lot of mass, it's going to have no trouble pushing the other objects out of the way. So this is what an integration might look like. So here I have it's a function that just moves all the bodies, and it starts by looping over each rigid body. And first of all, we check if the mass is not 0. If it is 0, that's what I use to define static bodies. So if you set the mass to 0, then in the minds of of the physics engine, it's just a static body. It's not supposed to move, so we're just going to skip over it. So the first step is to integrate linear velocity. And this was using the equation from before. We take the inverse mass multiplied by the force accumulator times a delta time, and this would be equal to the linear momentum. And the force accumulator can be thought of as like the net force of the body. So for instance, when you apply gravity to the body, it's going to add gravity to this force accumulator. But then also, when you interface with the physics engine, if you apply different forces to the body, those forces are just going to be added to this force accumulator. And that's
Is
how
there
we
a
update
reason?
velocity. Oh,
Is there a reason to multiply by inverse mass as opposed to dividing by mass?
not really.
Oh, okay.
It's just to make it similar to the next line where I have the inverse
Oh, that
inertia
makes
tensor.
sense.
I keep both the mass and the inverse mass and the inertia and the inverse inertia tensors. I keep those saved for the bodies because I use them a lot, so I don't have to recompute them, or I don't have to divide or whatever.
Oh, so the inertia tensor, you don't have to update that. That's like a property of the shape.
Yeah, at least the local inverse or the local inertia tensor is. The global inertia tensor has to be updated every time. And you can see I do that on the last line. I update the inertia tensor because it
Okay.
changes as the object rotates.
And that's the Q inverse that formula you had shown.
Yeah,
Okay.
that's kind of written out of this um, where that Q thing equation is really applied is whenever I update the inertia tensor. I just take the local inertia tensor, I transform it into world space essentially.
Okay, thank you.
Yeah. So yeah, I do the same as I do with velocity as I do with angular velocity. But this time, instead of the inverse mass, I use the inverse inertia tensor times the torque accumulator times set the time step. And this inertia tensor is a matrix free. This is a custom class that I wrote. So when I do this multiplication operation, it's actually doing a matrix vector multiplication. And it returns a vector, which is used to update the angular velocity. Then I zero out the accumulated forces and torques. So they don't persist for the next frame. And then we integrate positions. And this is more simple. This is just taking the velocity, multiplying it by the time step. And for the orientation, a little bit more complicated. But this was that axis angle equation that we saw earlier. So we take the axes of the angular velocity, we just normalize that vector, and the angle will be the magnitude of the angular velocity times the time step. And here is a little, this is just to make sure we don't, input if the angle is 0, then this vector must also be like 0 in length. So this would probably return like a nan vector or something. but this is like a check just so from axis angle doesn't freak out. And yeah, finally we update the body C-frame, which is that axis angle rotation multiplied by the body's C-frame. So we're rotating the existing rotation of the body by this change in rotation. And here we're just subtracting the position because we don't want to transform the position, and then we add the position in afterwards. All right. And
just to check, I'm not going crazy. Body C-frame position and body position are the same thing, no?
No, because the body position is updated here, so it's
actually. Oh, okay. I'm glad I asked.
So there's a slight, So with just this logic, and I hope everything makes sense so far. But with this loop and setup, we already have the ability to give motion to bodies. So I have like 3 bodies here. They don't have any collisions yet, but I can assign some initial velocities to them, and you can see that the blue one kind of goes up before it falls down, and the other ones are spinning. All right, so next I want to talk about the actual like physics flow, or the physics engine pipeline. Basically, the order we perform things in. So in my engine, I apply gravity first. I do this for the reason that if you, when you're interfacing with the physics engine, and say you're applying a force to some object, it's also going to happen before everything else. So why not apply gravity along with those forces right at the beginning? So yeah, the apply gravity and integration can be shuffled around. It doesn't really matter where they are. That's up to personal preference mostly, but these 3 in the middle usually or always come in this order pretty much. So the broad face and narrow face, the difference is in the broad face collision detection, we're trying to generate collision pairs. So we're trying to find objects that are close to each other, close enough that they might be colliding. We don't know yet because we don't want to, go through the overhead of calculating the exact collision detection. This is just like a preliminary stage where we just make sure that we don't check for collisions between objects that are like super far away, right? So only objects that are like close to each other. And the way you do this is usually with like axis-aligned bounding boxes. Those are those are a lot cheaper to check if they're overlapping or not. And they're pretty easy to compute too. You saw, we go back. If you want to calculate the bounding box of a box shape, you can use this function here. You just take the half extents and you take the rotation matrix components, and you can do a little bit of taking absolute values and multiplying by the sizes, and that way you can get the minimum and maximum, so it's very cheap to compute. All right. So that's for the broad phase. For the narrow phase, at this point, we already have the...
Sorry to interrupt. Just to be clear, I understand. So axis aligned means aligned to the global coordinate axis, not to the local axis of the particular object. Yeah.
Right, yeah. And when they're axis aligned, checking if they're overlapping, you can just take each, let's say the bounds of each axis and check if they're like greater or less than each other. So it's quite easy. Right. So for the narrow phase, at this point we have found the objects that are near and are close to each other. Now we come to the actual collision detection, and I've split this narrow phase up into two parts. One is to detect collisions, check if they're actually colliding, and the other is to generate contact points, and this will be important when we go to the resolution step. And contact points is points on the shapes, between two shapes, where they are colliding, because that's important too when we need to determine how we want to separate the shapes after they've collided. And that's what we do in the resolution step. We take all the contact points we've generated and we try to solve them. We push them apart. And I will talk about how we go about doing that in a little bit. And finally, we integrate the velocities and momentum and or the forces, which is what I showed you earlier.
So does that not depend on the stuff before it? Because you said you could move integration around.
Yeah, some engines do integration first and then do collisions. I think this is like the most common setup from what I've seen. But you can move this back here before you do the collision detection and
Okay,
resolution.
so the resolution isn't applying forces.
Right. No, yeah, it's applying forces, but it's not moving any objects. It might be changing velocities, but it's not changing any positions. That happens only in the integration phase.
Okay.
So if you move this back, essentially what will happen is it'll apply some forces, but then it won't be until the next frame that those forces will actually take effect.
Gotcha.
All right, so I'm going to talk about collision detection next. And there are many different algorithms depending on what types of shapes you're dealing with. And it really depends. If you have many different types of shapes, uh, you essentially need like a different collision algorithm for every like combination of shapes you can think of. So like here are three examples. If you have a sphere in a box, you need like a total of three um, algorithms. Now that's why there are some algorithms that are made to handle a wide range of shapes. There are some algorithms that can handle any type of like convex polyhedron or convex shape, really. But here, in my case, I have just implemented three distinct algorithms for every case. So for the first one is sphere versus sphere collisions. This is probably the easiest kind of collision detection. So here we have two spheres, and I have defined a few variables here. So PA and PB, those are the center of masses of the two shapes. Then we have two radii, so we have the radius of shape A and radius of shape B. And I've marked this red line to be the distance between the centers of the two spheres. And we can say that the spheres must be colliding if the distance between these two, the centers of the two spheres, is less than or equal to the sum of the two radii. And we can also, that's what I just said. We can also generate the contact points pretty easily. So, for instance, the contact point of shape A on shape B would be right here, essentially just the closest point on the sphere to the center here. And so the contact point on shape B to shape A would be right here. And the normal would just be the the difference between the two centers. So that way you can get both the contact points and the normal. And if we zoom in a little bit, we're also interested in measuring this distance right here. This is what we call the penetration depth. And this will be useful when we want to solve this this collision or this error. This will be a measure of how far we need to push the shapes apart to make sure they're no longer colliding. So that's why we want to generate these 2 points. We want to measure this distance.
Maybe this is skipping ahead, but do you just resolve that and then exert the forces, or do you have this be a soft constraint in some sense?
Yeah, so I don't solve it. I don't solve it immediately, and it is like a constraint exactly, which I'll get into. Yeah. So here's an algorithm in code form, what it might look like. And I'll go through this real quick. So we have some definitions here for the position of sphere A, its shape, and the radius, and the same for the for sphere B. We want to get the difference between the two positions and measure the length of this difference as well. And then we have the sum of the two radii. So if the distance is positive, what this means is if the distance between the two shapes is longer than the two radii, then the shapes aren't colliding, and we can just return from here. Otherwise, we set a new normal. We just initialize it to like an arbitrary direction, just in case if the spheres are like right inside of each other, like they share the same position, then this length is going to be 0, and that's going to cause some weird issues. So yeah, exactly. We want to avoid dividing by 0 when we try to normalize this diff here. So if the length is greater than 0, then we can set that normal. Then we measure the distance, which is the penetration depth, right? This distance right here. And negative means penetration. And so we want to find the contact point on the surface of sphere B in world space. So that would be one of these points. The other point can actually be generated just from this, and then from the normal, and then at distance, you can get the other point. So we only really care about getting 1 point. And finally, we add it to what we call the contact manifold. This is it's just a collection of contact points, because there could be multiple contact points for a given pair of collision shapes. All right, moving on to Spherebox collisions. So here again, we have the PA and PB. We have the centers of the two shapes. We have the radius RA. And what we're going to do here in this case is we're going to transform the sphere's position into the local space of the box. So this is essentially just changing the problem into an axis aligned, a sphere versus an axis aligned bounding box instead, which makes the problem much easier. And then we want to find the closest point inside the box to the sphere. And to do that, you can just clamp the sphere's position to the bounds of the box. So in this case, on the x-axis, it doesn't get clamped because it's within this range, but on the y-axis, it's above here, so it gets clamped down, and that way we can find the closest point. And again, we generate the two contact points. And we can also measure the difference or the penetration depth, and that can just be done by taking the radius of the sphere and then subtracting the distance between this closest point we found and the center of the sphere. And then we can just transform the thing back into world space, and then we can again calculate the normal in world space and all of that stuff. Right, the normal. And this is it's kind of similar to sphere versus sphere. We just, instead we have a sphere shape and its radius, then we have the box and its half extents. And then we have the sphere position. We transform this into the box's C-frame, so into the object space of the box. And then we just clamp the position into within the sizes of the box. And we can calculate the distance between the two, between the point on the box and the sphere's position. And we can, again, back out if they're not colliding. Then we transform it back into world space, and we calculate the normal from the difference. And yeah, and we're also transforming the difference into world space as well. So we get the world space normal, and then again we get the penetration distance here, and we can report a contact again.
I'm a bit confused about when you report these contacts, it seems to have lost the context of what kind of objects were colliding or no. I mean, how is this actually going to be used to resolve the collisions if... How is this list of contact points going to get used?
Yeah, I'll get to that probably.
Okay.
But this manifold is saved in the collision pair, so and it also knows which shapes it is. Yeah, it's passing a manifold here. It's kind of a weird.
Okay, but this is
Yeah.
one of these for every contact. It's not like a global thing that's remembering all the contacts.
No.
Yeah. Okay. Thanks.
No, it's just yeah. Each pair, each collision pair, has a manifold which stores the contact points that belong to that pair of collisions or of collision shapes. Finally, I want to talk about box collision. This is more complicated because there are a lot of different edge cases. And for this problem with these two boxes, we're going to solve it using something known as the separating axis theorem. And the separating axis theorem says if we pick some axis and well, it says if the boxes are overlapping, then they're inseparable by a line. Essentially, it's pretty simple. If there is no overlap, then it's possible that there exists some axis that can separate the two boxes. So we could use this algorithm where if we pick some axis and we project all the points of the two boxes onto this line, and then we want to see if there is some overlap. And if there is, we can go to check another axis and do the same thing. And we will do this for every edge direction. And the idea is, if there is one of these axes where there is no overlap, then the boxes don't collide because the boxes must be separable. And so we can also, if we record the overlaps for each axis, and we take the axis that has the least overlap, then we can also get the normal. So in this case, the axis would be this one right here. and if we project down onto that, then this tiny little distance here would be the penetration depth, or the minimum penetration depth, and so the normal would lie along this this edge here. All right. So it gets more complicated in 3D. So first of all, we have 6 edges to check instead of 4, as we saw here. And also in 3D, we actually have a few different cases. So we can have a case where we have the corner of one box intersects the face of the other box. And then we also have edge versus face, and face versus face. And then there is also a sneaky little case where the edge of one box collides with the edge of another. And actually, for this case, this one can't be solved with just these two or just these edge directions. You need a few more directions for that. You actually need to take the cross products between edges. I'm not going to go into too much detail on that, but it essentially means you need like 9 more edges. Actually, this is false then. You need like 9 more. So you need like 15 edges to check in 3D, or 15 directions or axes to check in 3D. The reason you need those extra cases is it would be fine if you just wanted to check if they're overlapping, but because we also need to check we need to know the collision normal, which in this case we would expect to point like in this direction. We need those extra cases to find the actual minimum penetration depth.
Thanks, that was clear. Yeah, I was a bit confused, but that makes sense.
Yeah.
Is there is corner versus corner like just too rare to care about?
It can never happen, pretty
Never
much.
happen?
So
Okay.
yeah. Well, it can, but it's like
1 millisecond
case,
before edge versus edge or something.
it's probably just going to pick one of the faces as the normal in that case, and just go about it that way.
Gotcha.
So in 3D, after we've calculated the normals and the penetration depth, we need to find the contact points. And the problem is there can be multiple contact points. There can actually be up to 4 for a box. If, for instance, if you have a face, or if you have a box resting on top of another, you want a contact point here, one here, and also one behind, right? You want a contact point for each corner.
Why do I want that? I mean, the force is orthogonal to the box surface anyway. Why do I care that there's 4 points?
It's easier to do that. And also, if a box is like resting on the edge, right? If you're, let's say you're having a box resting on top of this block and you push it, right? Yeah, you need torques and stuff. So yeah. So you want to identify what we call the incident face, which is the red one I've drawn here, and the reference face, which is the pink one right here. And the reference face is orthogonal to the normal. So this would be like the face that we're colliding against. Like in this scenario, this face here would be the reference face. And I know these two boxes aren't colliding, but it's just for just to make a point. And so what we want to do is we want to project the points from the incident face down to the reference face. And then that gives us a rectangle and a quadrilateral. And what we can do then is we can find the points where it intersects. So both where the lines intersect the rectangle and also the vertices of the quadrilateral. And this gives us, in this case, a total of like 1, 2, 3, 4, 5, 6 points. And then we want to prune a few of the points. So points that we want to prune, if a point lies outside the rectangle, we don't care about it, we can throw it away. If one of the points, like in this case, if there are points that have a positive penetration, right, that aren't going into the rectangle, we can prune those too. But let's imagine that this is actually, like, this entire face is actually resting on top of this box. In that case, we would like to go in a scenario where we have 4 points instead of 5. And so there's like a heuristic and an algorithm to choose the best or choose the 4 points that best fit the set. And once we have that, we can find the contact points, and the normals of these contact points will always be the same. And that's how Boxbox collision works, basically. So, sequential impulse is next. So this is about the resolution step. So we're now at the step where we want to solve these contexts that we've gathered. So in my physics engine, contexts are modeled with constraints. So everything is constraints, which includes contact constraints, as they're called, that are used to push objects apart. We also have friction constraints that like they add a little extra force to prevent objects from sliding. And yes, we model everything as a constraint. So mathematically, a constraint is of the form c equals 0, where c is an expression representing the constraint. So in our case, we would want to express c as a linear combination of positional properties like linear position and angular position, aka orientation, and for joints, right? So for contact points, we would want to contain positional properties from both rigid bodies. So the part of our code that during the resolution phase make sure all the constraints are satisfied is called the constraint solver. And the most popular method to solve constraint is called sequential impulse. And sequential impulse was popularized by Aaron Caddo. He's the author of Box 2D, which is a 2D lightweight physics engine for games. And so directly manipulating position properties of rigid bodies to satisfy constraints is a bad idea, because that results in excessive jitters and your game would probably look bad. So instead, Aaron Caddo proposed that we derive the expression for C, or the constraint, so to differentiate it and to get the corresponding velocity constraint, which we then solve for. So a velocity constraint between two bodies is modeled as a linear combination of the linear and angular velocities of both rigid bodies, plus a bias term, where V in this case is a 12-dimensional or 12 by 1 matrix, a column vector. And each of these terms, so VA is just the velocity vector of object A, the angular velocity of A, velocity of B, and angular velocity of B. So this is all put in a long 12 by 1, or yeah, 12 by 1 column vector. And J is what we call the Jacobian matrix, and this contains the linear combinations for each of these terms, or each of these components. And then we have a bias term, and I'll get into the bias term, what that's used for later. So we're going to take a bit a leap of faith here and say that the required change to solve this constraint, right? We want to solve this constraint. The required change is equal to m to the power of -1, or the inverse of m, times the Jacobian matrix transposed, where m is what we call the mass matrix, which is this huge 12 by 12 matrix of all the masses and inverse or the inertia tensors of the objects, where MA is just a diagonal matrix with M with the mass of A, the scalar mass of the object all across the diagonal. And so the inverse of that matrix would be this matrix here. We just take the inverse of each of these 3 by 3 matrices. And
Sorry, can you just go back 2 slides and let me look at J again? Oh yeah, that one. Okay, thanks.
Right. So if we assume, or we know, well, we assume so far that the required change to solve this constraint is proportional to this this matrix here, or this vector here, then we're going to define the proportionality to be the what we call the Lagrange multiplier. We define that as lambda. And so this would be the required change to solve the constraint. So we substitute delta V with that expression, and we want to find, or we want to solve for lambda now. So we can do this by, first of all, expanding this. So we get this formula here, and then we subtract JV and the bias term from both sides. And we can realize that this this right here, this J times m-1 times J transpose, this would be equal to a scalar, so we can actually just divide this on both sides, and we get a solution for the Lagrange multiplier, or lambda. And now we can solve the constraint. So we can have the solution for lambda. If we apply this change, we can solve the constraint. And there is an analogy. I know this is a lot to take in. There's an analogy between this expression here and point projections. So you can recall that if you have an equation like this would be a plane, right, in 3 dimensions. And a plane can be defined as from a normal n, where the normals, say the normals components are a, b, and c. And if we have a point x, y, c as a column vector, then we can rewrite this equation as the dot product of these two, essentially, plus a bias term, right, which equals 0. And you'll notice that these two actually have the same form. Now, if you imagine that we have a point that doesn't lie on the plane, right? So if this doesn't equal 0, then the best way to, or the best way to project, or to make this point go on the plane, is to project it onto the plane, and you can do that using the normal. So if we have a point that isn't on the plane, we can put it on the plane by taking the normal and then take proportional to some multiplier, which is similar to what we saw earlier with the Lagrange multiplier. The difference is, instead of just applying the Jacobian, because objects can also have different masses and different inertia tensors, we also have to modify this by the mass matrix, and this gives us the final equation. So I hope that made sense. Yeah, I don't know if we're running out of time, but I have a little. I have deriving it for contact constraints also.
I think you can continue. There's a half-hour break in the schedule now, so there's no rush.
Okay. So for contact constraints, let's say we have these two shapes here. We have a box and a circle or a sphere. And so we have the two contact points, PA and PB. And we also have the contact normal that we generated earlier. And we also actually want to get the tangents to this normal. This is something I calculate when I do when I calculate the normal as well. These tangents are used for friction, which I actually haven't covered, but those are pretty useful for friction too. But for now, we're just going to focus on the normal.
How do you decide on the sign of that tangent? Which direction? Or, I mean, if it's a plane, as it is in this case, if it's a box and a sphere, maybe you don't need the particular direction.
Yeah, it doesn't really matter, because when at least for friction, when I apply friction, I just apply friction along one of the tangents and then along the other tangent, and then the combination of those two will be
right.
Yeah.
Oh, I guess you're only using friction in a formula that has the velocity of the object in it anyway, so you just want to be opposed to the direction of the... Yeah, okay.
So we can create a contact constraint from this. So we'll see that so the first contact point PA would be equal to the center of the box plus this distance RA, and similarly for PB. And our constraint says, well, if we take the vector from P to A, we want this vector from P to A to point along the normal. Essentially, we want these points to be pushed apart so that this vector will point along n, which is why we use the dot product. So if this dot product is greater than or equal to 0, then we have successfully separated the two contact points. So we can substitute in with PA and PB, and so we get the full expression here. And do notice that this is like an inequality constraint, right? We have greater than or equal to, because it doesn't really matter if it ends up greater, and it might end up being greater as we solve the constraints. Because the whole idea behind sequential impulse is you solve these contact constraints one at a time, and then you do that over several iterations, hoping to like converge to a global solution, essentially. Because what you could have done instead was you could have actually just put all the contact constraints into like one big matrix and solve all of them at once, but that's super expensive and not very viable. So we solve them one at a time, and eventually will converge to a global solution, hopefully. So this might end up being greater than or equal to 1 as other constraints are being solved, and they push other shapes around.
Is there any... I mean, you resolve these collisions in a kind of order that remains fixed between frames, or is there any value to kind of making that stochastic at this point with collisions? Or how do you decide which pairs to do first if there's an order to it?
Yeah, that's... I don't have any like stochastic thing to it. It just solves it in order. But it looks fine, actually. But yeah, it's that when you have multiple objects, like if you have like a tower of blocks, then solving the constraints between two objects might push those objects into other surrounding objects, right? And then those are going to solve, and then they're going to push into other ones as well. So, and that's why you run multiple iterations. Eventually, you hope, or hopefully, you reach a point where all the boxes will be separated equally.
But how do you... I mean, I guess I didn't see any kind of cutoffs in here, but presumably, you push the box off, but it's never going to be exactly 0. It will be, some epsilon above, and then gravity will pull it down, and then the collisions will push it up. How do you stop that kind of oscillation? Or is it just that it's so slow to resolve the collisions relative to everything else that it never quite gets out of the other object or something?
It'll always, or when you solve between two objects, it will always push them like completely apart immediately. Or it won't push them apart, but it'll solve the velocities, which I'll, yeah. I'm not sure if I understood your question. Oh, okay. Yeah, what I was going to get to is, like I mentioned earlier, manipulating the positions directly is not a good idea. So we want to derive this, take the derivative with respect to time of this positional constraint to get the velocity constraint. And here we get the... so for the centers of the objects, if you you take the derivative with respect to time, you should get the velocities. And for the r's, you take the derivative, you get the angular velocity cross product with the distance, or the r. And so you get this whole expression here. And this is the equivalent velocity constraint. And so where you get this, where J becomes this Jacobian matrix with -n for the linear parts, and then for the angular parts we get RA cross n and RB cross n. This doesn't make any sense, does it? I don't know. Yeah. Yeah, so we can calculate the Lagrange multiplier, and then we can find the required change to this V, which will solve the constraint. And yeah, that's pretty much it. I had a little bonus video. This was like Roblox physics overlaid with my own, just to just to compare them, I believe the red blocks are Roblox, and the green, or no, the red blocks are, let's see. Yeah, the red blocks is Roblox, and the green are mine. They're kind of similar.
Oh, that's great. Can you play that again?
Yeah, yeah.
Oh, that's cool. How? I mean, obviously, there's a lot of scope for being more sophisticated about various things here in various axes. But how fancy do you think the Roblox physics engine is in terms of making use of? I mean, the applied math literature is just full of tricks for. You can do various things like take half step Euler, or there's various other things. Do you think they're more or less doing the simple thing, or is there like layer after layer of very fancy ideas going on in their engine?
Yeah, I think there are definitely many more tricks in there, but the basic like concepts are there. Like most physics engines, I believe, solve like contact constraints like this. You can also like combine multiple constraints together to solve them together. For instance, if you have like a prismatic joint, you could solve that as like first a positional constraint and then also a rotational one that limits it to only rotate around one axis. You can use like bigger Jacobian matrices for that. But like there are many other tricks, and like it is very much like a bunch of like little tricks and stuff. Little optimizations.
Yeah, that's really interesting. Thanks a lot for that. That was very well prepared. Thanks.
That was awesome, Mathias.
Thank you.
I wanted to ask you. I'd seen your Twitter. You'd shown like a display of the tennis racket theorem. Is that like just kind of an emergent thing from having the inertia tensor, or do you have to do anything special for that?
Yeah, it's almost emergent. Actually, to get that effect, I had to set an angular velocity, or I had to set an angular impulse, and then update the angular velocity from the angular impulse directly. So if you want to get that, I think you have to record the impulses, or the angular momentum. Sorry. But otherwise, like just the effect that let's see if I can find it. The effect that this depends on this global inverse inertia tensor, which also updates every time the object rotates, is essentially what creates that effect. I think as long as an object is spinning along its like second moment of inertia, or its middle like moment of inertia, it's gonna cause that effect, where it's gonna like flip momentarily.
Oh, okay.
Actually, fun fact about that: that was something the Russians, I believe, discovered. Like Russian astronauts discovered, and they kept it secret for years because they saw the spinning object and thought, well, okay, we're living on, an Earth that's spinning as well. So is that also going to momentarily flip and cause the southern hemisphere to turn into the northern one? So they kept it secret. They kept it confidential because, yeah.
Maybe they could figure out how to drop a bowling ball on the exact spot on the Earth.
Yeah. Luckily for us, the Earth is more heavy on the equator, so we're spinning along the third moment of inertia, which is stable. But theoretically, if we could concentrate enough mass, if we could remove, like, or terraform Earth, we could make it happen.
Oh, that's cool. Yeah, we should. One should teach these physics experiments in VR in Roblox someday. Cool. All right. Shall we leave it at that? Thanks, Mathias.
Yeah, sure.
Thank you.
Thank you for coming.